Good afternoon, everyone. Today's talk will be given by Professor Manikandan on the topic Cryo-CMOS circuits and systems for quantum computing applications. To give an abstract about the topic, present-day quantum computers comprises of 200 qubits operating at 10 millikelvin temperature with a controller and readout circuits for each qubit operating at room temperature, which is 300 Kelvin. Typically, each qubit requires 3 dedicated wire connections running from the room temperature electronics to qubit to perform X, Y, and Z control, and to perform data readout operation, a total of 300 wires for 100 qubits. To realize a scalable fault-tolerant quantum computer with greater than 1000 qubits, the dense wiring connections required between the room temperature electronics and the quantum processor placed inside the dilution refrigerator serve as a limiting factor. A fully integrated qubit controller and readout electronics operating at 4K temperature is a potential solution to place the interface electronics closer to a quantum processor inside the dilution refrigerator, thus reducing the wiring overhead. In this talk, potential modeling challenges of the semiconductor devices at 4 Kelvin temperature, analog circuits used in qubit controller and readout electronics, and its design challenges will be presented. To give you a brief bio about the speaker, Manikandan R R, Professor Manikandan R R received his Ph.D. from Electrical Communication Engineering, Indian Institute of Science, Bangalore in 2014. His PhD thesis focuses on low power and low spur frequency synthesizer circuit techniques for energy efficient wireless transmitters. From 2015 to 2016, he worked as a lead design engineer in Cadence Designs Systems, Bangalore, and designed frequency synthesizer circuit for SERDES applications. From 2016 to 2017, he was a member of Kilby Research Labs, Texas Instruments, Bangalore, and designed ultra-low power analog circuits for an IoT power management application. From 2017 to 2023, he worked as an analog design engineer at Texas Instruments and designed isolated power and data transfer circuits and precision analog circuits. Welcome to this.
Thanks, Korea. It's something new, and it may take another maybe couple of 3 more decades to be in practice. But even before the computers are there, researchers have started designing algorithms for a computer which is not being present, things like that. And so the problem has to be addressed in multiple dimensions, in terms of hardware, in terms of algorithms, in terms of physics nature of the problem. So the researchers are attacking the problem in all directions, and it has to finally fall in place, things like that. So today we will look at what kind of circuits are involved in these kind of applications. Okay. So to begin with, on fun note, this is a quote from Avengers movie. I think most of you are aware here. Because the domain is most related to quantum physics, we are not physics engineers, we are not physics scientists, right? But what do they have? I think that is sufficient for us to understand the domain, like only for conversations. Okay. And next thing is, if you are going to enter into this field, I think there is going to be quantum word in every line you go through. I try to avoid the second point here in this talk. Let's see how we connect. Okay. So with that, I will go into the technical presentation. So if you are going to build a computer, if you are going to build even a normal binary classical computer, you need a bit, you need an information holding device, bit or something like that, right? So you have to define a bit, and you need to, you should be able to control the bit. That means you have to read or write data to the bit. Okay. Once you have that capability, then you build on the computation, logic gates, things like that. Then you come into algorithms, then you form a system. You form a, like whatever Intel i5, i6, i7 core, what you have today. It has gone through all these phases. Today, quantum computer is in the very early stages of, in the definition of a bit, in the definition of hardware, in the definition of algorithms, things like that. Okay. So we will go in that order. We will try to identify what is a bit, quantum bit. Then we will understand how to control the bit. I mean, how to write information into the quantum bit, how to read information from the quantum bit, how to manipulate the state of the bit. Then we will build logic gates using the bit. Once you come to that, how a quantum computer looks like. So all these things will go step by step. And all these are experimental, not algorithm theory, things like that. So let's, when you say experimental and these are in beginning stages, a lot of calibrations are involved. Things will work under certain conditions only, things like that. There will be a lot of ifs and buts, but we are in the beginning of the hardware for the quantum. Okay. So let's start with defining a bit. So the bit in quantum domain is a electron. Okay. How do you when you say bit in your classical bit information will be state 1 or state 0 using a logic gate, right? Now you have to define a similar information using the electron properties. Okay. The basic property of electron is the spin of an electron. Okay. So when you leave electron freely in any surface, it will have in some random arbitrary spin orientation. Okay. So if you can control that spin information, say spin up as logic 1, spin down as logic 0, that is how you are defining a bit. Okay. So if it is only that, a classical computer is already doing that. What is fantastic about this? So if you look at this here, this is the three-dimensional rotation sphere, you can call it as. So if you place an electron, if you map up electron rotation around this sphere, if it always in one direction, spin up or spin down, that is how we are clearly defining as logic 0 and logic 1. But the electron can sustain spin in other orientations, other angles as well. Okay, so in this case, if you can, it is a three-dimensional property, so it can maintain a constant spin under given physical conditions. Even this can be a legitimate state. Okay, so there are many intermediate states also possible if you are going to work with electron as a bit device. Okay, so now we said but we will stick most of the time to logic 0, logic 1. Let's see how we will use intermediate states as well. Okay, but if you want to define the intermediate state, you need to define theta and phi, or you can say any time, at any given time, the state of the electron is given by superposition of state 0 and state 1. The superposition coefficients are determined by alpha, beta, and which is function of theta and phi. Okay. Now, if we said we will use spin of an electron as a bit information, right? So we need to define logic. If you have one bit system, one qubit, you can have logic levels like 0, 1, and superposition of alpha and beta, right? So if you take one bit system, you need to define two numbers, alpha and beta, to identify what is the state of the electron is in. Okay. But if you take a classical one-bit computer, it is only one number, which is 0 or 1. One bit, one information needs to be, one number needs to be identified. In case of qubit, you need to define two numbers needs to be identified. Similarly, if you take a two qubit system, 2-bit operation, for a classical computer case, you need to define only B0, B1, say only two numbers needs to be defined. In this case, bit 1 can have alpha 1, beta 1, bit 2 can have alpha 2, beta 2 typo. So for to define a 2-qubit system, you need 4 numbers needs to be identified. Okay. So what it says, compared to classical computer case, which is a n-bit classical computer, you need information encoded in n bits here, right? So if you take a n-qubit quantum computer, the information encoded in 2 power n bits. The information diversity is in exponential increasing case. Okay. So how does this help? Let's say you are working in algorithm and you have your complexity of your algorithm is order of exponential. Okay. That is when executed in a classical computer. Okay. If you execute the same algorithm in a qubit in a quantum computer, the order of the algorithm will boil down to polynomials. So it can execute the algorithm in a quick and efficient way because of the exponential increase in the information density. Okay, so it simplifies.
Uh, so one difference also seems to be the amount of space that might be required to store those alpha.
Yes.
Like in the classical case, it's just one bit, but this alpha and beta are real numbers, aren't they? So it will take more space to store them. Is it not the
correct.
case?
That is right. The that complexity is pushed to classical electronics. That electronics what we use to write, say, define the address or something like that, right? So that information is moved to the classical domain. But if you once you achieve that, once you reach that, I have the capability to store that information and things like that. Because of reduction in the order of execution of the algorithm, this is very useful. This is worth taking that pain. So this is the background about how you are going to use electron spin as your binary bit. Okay, so it's not called binary bit; it should be bit, qubit. Okay, so now going from here, when you use a classical logic gate, you will define logic 0 as ground, logic 1 as VDD, 5 volt, 3 volt, things like that. You are giving some physical definition to the value of the bit, right? Say in terms of voltage in that case. In this case, electron spin pointing upwards, pointing downwards are differing by a energy quantity. Okay, so let's see how ones and zeros are represented into physical constants. Like in place of voltage, what is it here? So to go there, we are going to use these three constants, these three physical constants, and it is very fundamental. Every physics problem you solve, these are unavoidable. Let's say Planck's constant, Boltzmann constant, Bohr-Magneton constant. Let's see in the next slide. Let's use this information. I'll try to keep it very simple so that we all can understand. Okay, so what we are doing is we are taking an electron which is spinning upwards. Okay, let's say we define this as logic 0, something like that. Now, if you want to change the orientation of the spin pointing downwards, means then we need to add some energy to this electron. Okay, to the orientation, the spin orientation can be manipulated by adding or removing energy from the electron, and the additional removal of energy can be done by using microwave radiation. Okay, so whenever you write one or 0, you push in some voltage, push in some charge into the cap or things like that, right? In this case, you are going to place this electron under a magnetic field. Okay, so placing an electron which is in 0 state in a magnetic field which is given by h nu, E equal to h nu. So the amount of energy needed to change the state from, or to change the orientation from pointing upwards to downwards, this is called Zeeman constant or Zeeman split phenomenon. Okay, so just keep it. These are maybe it's very basic, needed, one time needed, and it has to be there with you so to understand the further concepts. Okay, so there is something called Zeeman split phenomenon, which is if you take an electron which is pointing up, which is spinning upwards, the amount of energy needed to completely shift it 180 degree, that energy is called Zeeman energy, and this is given by G mu B. Okay, so here mu is the constant, G is a fitting parameter, B is the magnetic field under which this electron is placed. Okay, so when you place an electron, it has to be under some magnetic field for it to even rotate. Okay, so how do we get that magnetic field? There has to be a constant magnetic field, and there has to be a programmable magnetic field. Two items you are seeing here. The constant magnetic field can be given by your fridge magnets, which is constant magnet, which is not alternating. Okay. If you take fridge magnets and all, it will be in micro Tesla, things like that, or even pico Tesla, things like that. Here, we need 1 Tesla. The numbers are very, very high, highest magnetic field possible on Earth. Okay. So if that is 1.3 Tesla is the maximum field possible on Earth, that is given by some element called neodymium, something like that. Okay. But if you, for our calculations, let's assume we are going to define this bit and we are going to place the electron in 1 Tesla magnetic field. Okay. So if you do that, here B becomes 1 Tesla, G is a constant. This is your Zeeman Zeeman split constant that is needed to change the orientation of the electrons. Okay. So this is an important thing. This is how we are going to change the orientation. If you give half the Zeeman energy, it can be 90° parallel to B also. It can, so you can give sufficient. You can get whatever orientation you want by adjusting the value of h nu. H is Planck's constant, nu is the frequency. That means you can change the frequency of the radiation around the spin around the electron spin, and you can change it to whatever spin you want. Okay. So the programmable parameter is here is h nu, and this has to be, all the system has to be placed in a constant magnetic field. Okay. These two are important points. Now, let's, yes. Where is it? Oh, here. Okay. Okay. So whenever you define 2 logic levels, you want to maximize the noise margin, right? You will have maximum VOH minus VOL, things like that, right? You can think these two are the 2 logic levels, and you want maximum difference between them for proper functionality, things like that. Okay. So that is the reason we are maximizing B. Yeah, otherwise, you could have kept a small magnetic field and you could have worked around this region. Okay. So you need the 2 levels to be defined very properly. So one way to do that is by increasing B. Okay. So given that we are headings are not visible, but given that we are having a 1 Tesla magnetic field, we are placing this electron in the magnetic field. So the energy difference, the first column, focus on the first column, the energy difference to change the spin down to spin up. This is Zeeman energy. If you just plug in the numbers to, this is the Zeeman, this is the Bohr magneton constant, mu B. So you just plug in these numbers, you see this energy is in 10⁻⁻25 joules. It's very, very small. Okay. So this is the energy difference between 2 states. Okay, it is not 5 volt, it is not 1 volt. Now we are talking 2 states which are separated by 10⁻⁻25 joules of energy. Okay. So now, okay, so this is the difference between 2 states. Now, what is the radiation frequency I want to change state 0 to state 1? Okay. So that is given by this E equal to h nu. Again, h nu should satisfy this value that boils down to frequency of 28 gigahertz. Okay. So we have taken an electron, freely spinning electron, and placed it in a magnetic field, constant magnetic field of 1 Tesla. If you do that, the logic states are differing by 10⁻⁻25 joules. Okay. And to make logic 0 to logic 1 transition, you need to use RF frequency of 28 gigahertz. Okay. You have to focus this RF energy towards that electron. Okay. Okay. So this is the constraints with which we are working. This is the constraints with which we are defining our bit. Okay. Now, if you take any temperature, means any room temperature or anything, right? There is a lot of thermal energy also available. Okay. Even thermal energy can change the state 0 to state 1. Any energy available around the spin of electron can change the state from state 0 to state 1. Okay. So thermal energy is given by this Kb into T. K is the Boltzmann constant. This is Planck's constant. This is Bohr magneton constant. So if you find what is the temperature that needs to be maintained around this electron, so that the energy is not more than difference between two states. Okay, energy is 10 power minus 25, Boltzmann constant 10 power minus 5. This temperature boils to be around 1 Kelvin. Okay, so just by this calculation, this is minus 272 degrees Celsius. Okay, so our room temperature is 27 degrees Celsius. So you have to now you are taking an electron, you are cooling down to all the way down. The lowest possible is 0 Kelvin. It's not practically possible. So we are all the way cooling down to almost lowest extreme physical constraints possible. Okay. So we have taken an electron, we have subjected it to constant magnetic field of 1 Tesla. The difference between the two states boils down to this number. So you have to use this frequency radiation to change the states, and you have to maintain the temperature of this bit at this Kelvin. Okay. This is followable, right? This is okay.
I have a question again. So again, from a layperson's point of view, very difficult to visualize because I'm not able to visualize. So I'm trying to think of an electron hanging in the air,
Yes.
Pointing upward, let us say, and then I send it a burst of electromagnetic radiation.
Yes.
And it has to be just long enough so that it spins it, flips it,
yes,
and then stops. If it goes on for a longer time, it will probably flip it again.
Yes.
Does that happen?
Yes, that happens. So that burst needs to be controlled. The duration of the RF frequency focused.
Okay.
That also needs to be controlled. Yes.
Okay. And then the final issue is of observing the spin. I mean, how do I know which way it is?
We'll come to that. We have answers.
Okay.
We have answers for all the things. Means even though all this seems extreme, we are already having practically, we are seeing all these things. I'm just setting up what kind of background needed. So when you see the computer, you will be able to appreciate, yes, this exists. Okay, so these are the conditions. Now, we said we'll take an electron and we need to focus some RF radiations towards that electron, right? How do you do that? So first of all, you have to place an electron at some point. Okay, once you place that point, you run a conductor around it. Okay, a metal line around it. On that metal line, you use a AC current or AC voltage waveform just flowing in the metal line. Okay, if you have a AC current flowing in the metal line, according to right hand thumb rule, there will be a magnetic field around that wire. Okay, so if that wire is in close proximity to electron, so let's assume this is that wire and this is that electron. So if I put a AC current on this wire, it is going to generate a magnetic field around it, and electron will be subjected under that magnetic field. Okay, so what we are saying, we will first we will come to how we will place an electron at a point. We will come to that. Let's say we do that. We run a wire close to it and send RF signals in this pattern, so that this gains energy or this thing. Okay. Now, if you are talking about 2 qubits, you need 2 electrons separated by some distance. Okay, and each electron should have its own dedicated line, RF line, to enable it to absorb energy. Okay, and you can change the 2 frequencies so that this logic level difference can be different. This logic level difference can be also different. Or you can use instead of a constant magnetic field of 1 Tesla, you can use some slope of magnetic field or things like that. Okay, so what we are saying, so this is how it is going to appear. So let's say if you take this yellow, this is the representation of the spin. To begin with, let's say all are pointing up, which is state 0. If you use this frequency for let's say HF2, HF2 is needed to completely flip this to 180 degree and get logic 1. You can have F1, which is F2 by 2, or the power by 2, things like that, and you can say only pi by 2 shift like this. Okay, so instead of constantly spinning like this, now constantly electron will spin around y z-axis like this. Okay. Okay, so this is exactly the thing what we are going to achieve in a silicon. Okay, we are going to take a silicon. You in your MOSFETs, you would have made n plus regions, things like that, right? N plus regions is abundance of electrons. Okay, now we have to isolate one of the electron, bring one electron and place it in some of the substrate. Okay, so that is exactly done in these devices. Okay, the device dimensions are so small. Let's say these are the two electrons. These are the two electrons. These two electrons are trapped under a small area, which is say 100 nanometer. This can be less than 100 meter, 100 nanometer plus 100 nanometer area. In that region, you create a potential well. Okay, so the potential well such that the energy, so the electron is trapped inside this well. Okay, you build such potential wells by applying different potentials running on the metal lines at different locations. So you can have n number of wells with electrons trapped in each well. Okay, so what we did, from the abundance of electron, we brought one electron under a potential well. Okay, so this is the electron which we are going to use for computation, and we are going to make it spin up, spin down, spin in all possible ways, and we are going to read this spin, and we are going to make logic gates using this spin. Okay, so this is what we are going to do. So this is to do that. This is the step followed. Okay, so first, being a 3-terminal with single gate, you can define 5 terminal device where means this electron means where the RF pulses are applied to P1 and P2. Okay, for electron 1, RF pulse 1 H nu HF1 is applied on P1. For electron 2, HF2 is applied to P2. Okay, so and so once you do this, you can make this. You have to place this device under one Tesla magnetic field. Okay, this is your device. Now, this device you place it in a 1 Tesla magnetic field. Given that, then you apply 185 10 into 10 power minus 25 energy. It will point up. This will point down depending on what is the value of H. Okay, so this is how you define the state. Now, the logic operation is performed in a way that you can lower the in a classical gates, MOSFETs are acting as switches. So if 2 switches are on, you get VDD or things like that, right? So same, you have to enable the interaction. You have to enable the interaction between the logic transistors. Here you have to enable the interaction between the electrons. Okay, so by applying a constant potential, P1, P2 are RF potentials. By applying a constant potential in the middle plate, you can lower this potential barrier. Okay, once you lower this potential barrier, these two are in the very close proximity. They interact by its own electric in the magnetic fields. Means the electron spinning on its own have its own small magnetic field around it. So the interaction happens between them. And then once this happens, you remove the voltage applied at this point. Means you remove you get the barrier back. Okay, so during this interaction, whatever happens is your logic operation. Okay, this is okay. Yes. If you want to rotate 1 by pi by 2, 1 by 2 pi or 1 by pi to control the amount of rotation.
Yeah, so when you're putting the electrons in the different potential wells, so effects like quantum tunneling or something won't affect the experiment?
It will affect. If it is very small and it has enough energy, it can tunnel through. Yes, that is true. The conditions are maintained. This has to be calibrated so much that all these effects should not be there. Or if something happens like this, you have to do something to remove that barrier or things like that. It has to be taken care of. Yes. Okay, so maybe these references, all this information, again, I'm also new to this field. This is my literature survey for last 1 month or 2 months, whatever. Okay. And let's see, you can note down these references. You may also can go and read, or we will find a way to share this reference. States. Yes. How it is different. So here there is something called entanglement. Okay, so the intermediate states. Okay, one thing is superposition. That is what we have discussed till now. Okay, so when you make the two electrons interact, there is something happens called entanglement. Okay, that doesn't happen in the analog electronics. If you have multiple voltage levels and define a logic gate with multiple logic levels, it doesn't happen. Let's see what is that entanglement. Yes, that helps in the computation. So exactly we are at that point. This is the concept of entanglement. Let's say we want to create a XOR gate. Okay, in quantum domain, this is called a C0 gate, controlled NOT gate. Okay, so you have 2 bits. This is bit 1, bit 2. So again, if you see in the transistor implementation, this is bit 1, this is bit 2. What are the operations done here are definition of the bit. Okay, you define it, you rotate this by pi by 2, you rotate this by pi and pi by 2, things like that. Okay, so you are defining, you are making this electron spin to go to that logic level, right? That's all we do here in the definition phase. So whenever you see this box, this means we are applying some RF signal at this green gate, green colored gate. Okay, so you define the bits. In this case, the bit is defined not at 0 level, not at 1 level, somewhere in between. Okay, pi by 2 somewhere in between. Okay, and even this is very tough to control. It may not be exactly pi by 2. It may be slightly higher than pi by 2 or slightly lower than pi by 2, things like that. Okay, so let's assume that this is slightly biased towards higher energy side. Okay, if you assume this Q2 is biased towards higher energy side, and you are defining Q1, okay, Q1 gate with some low energy is 0, high energy is 1. If it is low energy and this is slightly towards high energy, whenever you have 2 electron spins opposite direction, it will continue to remain in that configuration. Okay, let's say because of if you take a Earth's magnetic field, there will be flux lines flowing around the Earth, like that, right? Same thing you can assume again around the electron also. If the electron is spinning up, let's say magnetic flux starts and goes up and comes down. If the electron is spinning down, it comes from bottom and goes up. So if these two aid each other, they remain entangled. So this is called entanglement. Okay. So this phenomenon doesn't happen in analog circuits. There are some advantages to this entanglement phenomenon. Okay. So what we are saying, this is let's say this is biased around some.
Can we interpret it as saying that if there are 2 electrons oriented in the same manner and they are in proximity of each other, the amount of energy to flip any one of them will be significantly higher than what is required to flip it otherwise?
Yes, that is right. Okay. Or you can say that if you don't apply any energy to electron which is pointing down or some intermediate state, it will automatically align to the orientation of the other electron, which has got that energy. So that is called entanglement. Let's say if this is with a slightly higher energy, that means Q2 is having slightly higher energy. Now, if you give lower energy to Q0 and make them interact each other, this is zero energy, this is slightly higher energy. So they will automatically orient between themselves, one towards higher energy, one towards low energy. Okay, that means the state is still not changed. The state is still maintained, except it has gone to the proper energy levels, if you say that. Now, this is slightly higher energy. If you write very high energy above this, this will change its spin to opposite direction and give a flip in the spin of in the orientation spin. Okay, so this phenomenon, this is called entanglement, because if you have energy 1 greater than energy 2, the electron which is having higher energy will influence the orientation of the other and make it go in the opposite direction. Okay, so this bit flip, this is called bit flip. So, and this characteristics is similar to XOR gate truth table. Okay, so if you can say that if you have this configuration of 2 electrons biased with whatever, means programmed with whatever energy levels, when you make them interact and go back, the bits will flip or not flip based on their starting state and with a function of XOR gate. Okay, so similarly, this is a C0 gate. Not all digital logic gates can be made here. NAND, NOR, no, it's not possible. They have their own set of logic gates. Like given this fundamental behavior, they have defined, quantum algorithms have defined their own logic gates. So that is where the classical algorithm needs to be changed to quantum algorithms before programming a quantum computer. So their logic gates, their set of their instruction set, everything is different, aligning to the fundamental phenomenon of physics. Okay. Okay. So this is, we know how to trap an electron. We know how to program 1, 0 or any other level. We know how to make it interact and get some function out of it. Now the last operation is to read what is the result. Okay, so you have done this step. Now next step is how to read that step, what has been there. Okay, so focus only on this portion. Say you read, this is an electron pointing down, this is logic 0 level and this is logic 1 level. Okay, the energy difference between them is 10 power minus 25 joules. Okay, so this is the 2 states of electron. We have an electron which is pointing down. Okay, so you can DC shift the energy of the both logic 0 and logic 1 by adding a voltage source, like in how you do in a digital, right? So same thing, if you increase the DC potential around this electron, the entire logic level can be moved up or down. Okay. Now, if you have a reservoir of electrons, this can be your N plus region in your MOSFET. N plus region is abundance of electrons, lot of energy, right? This was very low energy, so we are shifting single electron energy close to a N plus region kind of an energy. Okay. Now, if you place this energy exactly at the midpoint between high and low, if there is an electron spin down, which is low energy, there is no jumping or sharing of electrons between them. You can treat it like a 2 capacitors which are unequal voltages. When you short it to them, equal voltages will happen. It will settle to equivalent voltages, right? And define a new voltage level. This is same phenomenon, except here it is 2 energy level. Means you have the left side is the reference energy level. Right side is you are shifting the energy level around the midpoint. Now, if there is a spin down electron, there is no sharing happens. If you have a spin up electron, the electron jumps and it will, to further equalize the energy, it will put 1 more electron to the lower energy level. Okay. So the upper energy level, which was electron spinning up, that is, we lost that electron. Okay. But the phenomenon happening here is there is a movement of electron. Okay. So whenever there is a spin up function is there, there will be a movement of electron. Whenever there is a spin down, there is no movement of electron. Okay. So this characteristics we will use to read whether the data is 1 or 0. Okay. So how do we do that? If now whenever this movement happens, you connect this plate where we connected the DC voltage. You can AC couple this gate to some, say, single electron transistor, some transistor, you can call it as like that. So whenever there is a electron movement happen, there is charge movement, there will be a transient voltage developed on V dot plate. Okay. Whenever there is a transient, there will be a momentary turn on of this transistor, and this will change the current IDS of the MOSFET. By detecting the IDS change, the blips of IDS, you can say whether the spin up was there or spin down was there. Okay. So this is current detection. Same thing you can do with impedance detection also. Same, the setup is same. AC coupling to a gate of the transistor. The potential seen at the drain will change whether the transistor is on or off, right? Or even a small potential is applied on the gate. So the potential change can be used to detect 1 or 0. If there is spin down, there is no charge transfer happens. So no potential change. Whenever there is a spin up and charge transfer happens, there is a potential change, and this will short or something like that, right? So this first one is called current measurement. Second one we can say RF reflectometry. So whenever there is you incident a RF signal onto some impedance, 50 ohm matched impedance, there is no reflections, right? But if the impedance changes because of some transients, there will be reflections happening, right, during that duration. Okay. So during this duration, the charge transfer happened, and at this time there was a reflected waves, and we have to detect that reflected waves through some low noise amplifier and things like that. So we have to use all our RF circuits concepts, reflections, transmission lines, low noise amplifiers, power amplifiers, to detect this readout, to make this readout. Or you should have a way to measure maybe a nanoampere or picoampere current change through this MOSFET. Okay. So 3 things. One is how the way to read it, spin up, spin down. You have to create a reservoir which is mid value between high and low levels. If the electron present is at low level, there is no sharing happening. If the electron present is higher level, then there is a movement, electron movement happening. Whenever there is a charge movement happens, there is a displacement current, or there is a transient current through the cap. So the transients we are using to detect 1 or 0. Okay.
What are the time scales and ampere scales?
These are in nanoseconds. So the logic gates are similar delay numbers. All these are because it is 28 gigahertz. The RF frequencies we are using are 28 gigahertz or higher gigahertz. The period is 1 gigahertz is 1 nanosecond. So if you can detect 3-4 cycles of this, then you are done. So your bit identification time is very less than single nanosecond, less than 10 nanoseconds.
And what is the that current that will be there?
For the amp, this current change, the current change is in nanoamperes. That depends on how big is this device. You can make it very big, low resistance path to ground. Low resistance path means more current.
Actually, again, it is probably because of our classical trained mind. It is very hard to imagine, like we have learnt of current as flow of electrons. And here we are talking about events happening within an electron. How do we get electrons flowing out of that thing?
Okay. So all these things, this is what is your quantum processor. This is not quantum processor. This is all classical electronics present outside. Okay. So your quantum processor is only these 2 dots. This is your processor area. This is your total processor, and this is the interface for the processor. Okay. So all you are doing is you are building the classical electronics around your processor. Means nothing but you are made a trace. You connected a wire at this point and routed it all the way to your room. So this processor was kept at 1 Kelvin. That is essential to reduce the thermal energy. now you have to get all these signals all the way up to our room temperature electronics to read or write or things to perform operations. Next slide, it is there. Okay, let's see the bigger picture, how it looks like. Okay, so now that we know, okay, we have a way to write, read, do logic operations. What is your quantum bit? All these things are defined. Let's say how it appears. This is how it appears. This is, yeah. Yes, correct. You lose this electron. Once once the operation is complete and you read the data, I think there is no memory to it. You just compute the algorithm quickly and then done. Yes, state is lost. If you cascade it, then the information propagates. But in the previous stages, it will be lost. Yes, done. Okay, I understand what you're asking. So in that case, I think we have to bring it to proper state, or even I think we don't have the capability to detect the intermediate levels. We will just get 1 or 0 kind of an output from that. So the output is in the classical electronics readable form. Okay, inside that computation happens, that is in the intermediate state. Okay. So the order, no, that's what we said. So if you take the penicillin drug, DNA structure, things like that. So that takes lots of years to give a structure for that. Let's say H2O means you draw a hydrogen atom, oxygen 2 atoms, and you make a covalent bond, all these things, right? If you want to do the same thing for penicillin on your own, you want to come up with penicillin formula using some computers, things like that. It is going to take decades. That is because of the algorithm has exponential order of complexity. Now, if you execute the same algorithm in the quantum computer, it has polynomial order of complexity. The answer can be quick. You can come up the solution quickly. That's all is the only benefit. Otherwise, for our normal operation, our classical computer is the best. Only for algorithms which takes lots of time, this is useful. Okay, let's see how it appears. So this is today's IBM quantum computer appears like this. This is the full computing system. This you cannot have something in your home. Okay. So what does this comprise of? One thing we said, we need to create a constant magnetic field and keep the electron in a 1 Kelvin temperature, right? So that is being done in this cylinder, what is kept here. Okay. So this cylinder, inside the cylinder is this stack, where your qubit is placed. This stack, if you see, there are different temperature regions: millikelvin, 100 millikelvin, 1 Kelvin, 3 Kelvin, 50 Kelvin, and finally out at room temperature electronics. Okay. So you place that 2 quantum dots, okay, that device at the tip and maintain it at 10 millikelvin. And below this, you can keep the magnets, constant magnets, which generates that 1 Tesla at the lowest layer of the dilution refrigerator. Okay, so once you get such a device, you place it in this place, and all the interface, all the connections to this, all these 3 gates, all the routings needed, same, all after this, whatever is present, everything comes outside this cylinder. Okay, so all these are connected, all these nodes are connected, tapped and taken through wires and brought as output. And this rack has the 28 gigahertz frequency generator, picoampere current measurement unit, low noise amplifiers. All the circuits needed are placed outside at room temperature here. Okay, and this is how a 2-qubit system, 2-bit quantum computer looks today. Now they are extending. If you are extending, they have a way to extend to 27 to 127, but that system had a room of equipments like this, and this dilution refrigerator become big, things like that. Okay. Yes. Yes. So we cannot give a step function change. It has to be done through stages, different stages of temperature. Like so, for example, this 50 Kelvin temperature is achieved using liquid nitrogen flow. There will be liquid nitrogen flowing around this chamber area. Millikelvin is achieved using liquid helium component. So only this region, it has to be liquid helium, gas or liquid. It has to be flowing. So it needs a different liquid helium should be separated from nitrogen and things like that. So you need to have the structure itself, the construction. By construction, it has to be done through different levels. Okay, so now if you are saying 27 qubits, 127 qubits, these are becoming room size data center kind of a thing. Okay, so one good question was how to we are defining intermediate levels and all, how to read whether it is exactly intermediate level, things like that, right? And even there will be existing magnetic energy disturbance, thermal energy disturbance, things like that. So this is very fragile. This bit is very, very fragile. So what the quantum error correction is very, very significant concept here. And by redundancy, they do it by redundancy only. In place of having 1 qubit, you do the same operation in 5 qubits and get the maximum likelihood, whatever probability estimate, right? So redundancy is being used very heavily here to improve the correctness of whatever is done. So if you see that, then 100 qubits, to do 100 qubit operation, you need 500 qubits or more than that with quantum error correction things. So the scale becomes bigger and bigger. So it is becoming impractical. Yeah. This is becoming impractical, means at least from the look, it appears to be impractical. Then what is the solution? If you see the state of computer today, it looks like this. There is a processor kept at millikelvin, and all wires come up, and there is a 300 Kelvin. At room temperature, you have all the equipments and things like that, right? Now, if this becomes, the problem is this becoming 500 qubits, and there will be so many lines. For 1 qubit, there will be 10 lines or things like that. Then 500 qubits, 5,000 lines. How do you manage all those things? And that 5,000 lines has to go inside the cylinder. Then the cylinder becomes big. If your cylinder becomes big, then the thermal control loop becomes complex. It's difficult to maintain a huge area of at 1 millikelvin, things like that. So this is called scalability. Going from 2-bit to 500 qubit, what are all challenges you face? That is the problems in scalable quantum computing. Okay. So the solution is move most of the electronics close to 4 Kelvin temperature. Okay. How do you do that? Here we are saying all this rack of instruments now needs to be moved to this under this cylinder in this region, right? So what do we do as an electronics engineer? You design the components needed, LNA, PLL, oscillators, voltage references, all the circuits needed to interface into a single integrated chip, make it a compact solution, and place it at inside the cylinder at 4 Kelvin temperature. Okay, what is the problem associated to your normal electronics? What you use design around you day to day is limited to minus 55 degrees Celsius. Your model files, your transistor behavior, your component behavior, everything is limited to in the range of -55 to 200 degrees C or something like that. We are talking about -273, -270 degrees Celsius. So we don't understand how a MOSFET will behave, how a resistor will behave, things like that, right? So if this is the solution, then you have to first develop models for your components, all the mom caps, mim caps, resistors, poly resistors, transistors, things like that. You have to develop models at 4 Kelvin so that whatever you design here, it will come as what you intended. Okay. So the problem one is there is no model for ICs at 4 Kelvin. So problem one is to define the models. Problem two is if you dissipate some power in this chip now placed inside the cylinder, that is going to create heat. Okay. If you are going to dissipate 1 watt of power, it can increase 10 Kelvin. It can change the temperature from 4 Kelvin to 10 Kelvin. That is, which was not there when all these are placed outside. Only wires were there, no power dissipation. You can easily maintain 4 Kelvin. Now, because you moved all the electronics inside, now maintaining this became problem. Then you have to come up with low power designs for your circuits, which don't increase much this. Okay. And we are talking about 1000 qubits, then you have 1000 such chips placed inside this. So if you are saying 1 watt per, you can maintain 1 watt you can allow 1 watt still maintaining 4 Kelvin. Then it becomes 1/1000 for 1000 qubits. So 1 milliwatt per chip. So you have to design an interface circuits, means all these signal generators, signal analyzers, LNA, and all these circuits which is present at room temperature has to be designed at 1 milliwatt power dissipation to place it inside this 4 Kelvin. Okay. So power consumption is main challenge. Device modeling is main challenge. So because these are very, very fundamental, this field is open. Okay. So this is what all the electronic engineers are going towards at present. In the future, you can have an option to integrate both in the same chip. The problem here is if you are saying 1000 chips here, 1000 qubits here, there will be 1000 lines between this layer to this layer. Even that is going to be issue, right? Then that interconnects can be through TS, through silicon vias, or it can be all integrated on the same chip so that even these 1000 wires between them can be removed. So this is the system level electronics problems, electronics engineers, what problems they face. This is giving new diversity of conditions to solve to come up with new solutions. To design at such low temperature and design at the same time at low power, still maintaining 28 gigahertz and nanosecond pulse widths, things like that. Okay. So this is all the problem statement. We have defined the problem statement, and only in the last 3 years, researchers have looked at this and proposed some solutions. Only in the last 3 years. Okay. Means I will not go much detail into this. So to generate, to know the model file, how a transistor will behave at 4 Kelvin, resistor will behave at 4 Kelvin, you need a characterization setup like this. Say, for example, in this, under this chamber, you place the device to which you want to generate a model. You want to model IDVDS characteristics or IV characteristics of diode or things like that. You place the device inside this, and this gives you this setup gives you the temperature, 4 Kelvin or 77 Kelvin or whatever, 50 Kelvin, whatever the number you want. Then you come up with the IV characteristics. Let's say first you characterize resistor, capacitor, inductor, BJT, MOSFETs. So to begin design, you need behavior of these components understood at 4 Kelvin temperature, right? So there are few publications in the last 3 years just to tell how these components behave at 4 Kelvin. Like that. Okay. So once you know this, then you can go ahead and build a 28 gigahertz LC oscillator. This power is still 10 milliwatts. Even one oscillator is consuming 10 milliwatts. So now we are talking about the entire system consuming 1 milliwatt. So this is all out and out open kind of thing. Again, voltage reference circuits, things like that. So this is just giving you the direction. I am not. I have lost time here. Did not go much into detail, but to give you what is the direction, what kind of design problems you work in this domain. First, you will try to come up with different models, at different temperatures, and ultra low power designs. Then total controller under 1 milliwatt power. So this is the biggest problem to solve, and it is not easy one to address. I will stop here. Maybe we can discuss offline on these works.
And for the very informative talk, maybe we need one more Samvaad-Talk to cover the rest.
This is the last talk, I think, in the running theme of, so you may have observed, those of you who have been attending the previous few talks, these were being delivered by some of our young faculty colleagues who have joined us in the last 1.5 years. So this was a theme dedicated to their talks. So I think this was the last one in that. So we have some upcoming very interesting themes. So please keep a watch on this space and be with us and attend the upcoming talks too. Thank you.